Hello, algebra students. We're going to spend one more day taking a look at quadratic functions, and we're going to use what we know about those and the equations from them to, again, describe some more situations. Specifically today, we're looking at several problems where we're trying to maximize revenue. We're trying to find the way that a company would use this in a practical application to be able to make the most money possible in a situation. So take a second and look at these. We've done one of these before. I want you to decide which graph you think doesn't belong with the other ones. And I'll tell you, I can come up with a way for each of them. So you can pause this if you'd like or make a decision right now. I'm just going to go through what I noticed about each one of these. Graph A is the only one where the y values don't change. It's got a slope of 0. It's a horizontal line, so the y's are always going to be equal to 2 on that one. For B, this is the only one of the four graphs that has a constant rate of change for the y's. The y's are increasing by 2 each time we move forward by 1 on the x's. It's got a slope of 2, right? It's got a very constant rate of change to get us a linear kind of a graph. C is the only one that it's got those individual points. This is called a discrete graph, but it's not connected. It's not continuous. That's the difference on this one. And D is a curve, just like C was a curve, but this is the only one that has a y-intercept that's not 2. All the other ones have a y-intercept that was equal to 2. So just something to notice about each of the graphs. And let's move on then. So we've got this company that sells movies online, and it's deciding how much they should charge to download a new movie. And they know that based on previous sales, they've got this prediction right here. And you know, this is kind of a balancing act for a company. The way to make the most money is when you can get a decent amount of money, but also a decent amount of sales. If you charge very little and you get a lot of sales, that's great. But if you're not charging very much, you're not going to make a ton of money. If you charge too much, fewer people are going to buy them. So you might be making more money per movie. But if you don't have as many sales, then that's an issue. So that's where we get this quadratic kind of a function that comes with this. So we're going to fill in this table. I'm using that 18 minus x to figure out the number of downloads, and this is in thousands. So remember, I'm substituting into 18 minus x. This is just 18 minus whatever my x number was. So I can go through, let's just figure out the number of downloads. So 18 minus 5 would be 13. 18 minus 10 is 8. 18 minus 12 is 6. And then that's a 3, that's a 0. And if it's just an x, I would just say 18 minus, oh yeah, look at that, it's x. The revenue, the amount of money that they make is going to be based on the price times the number of downloads. So 3 times 15 was done for you, that's 45. 5 times 13, that's going to give us 65. And remember, this is in thousands of dollars. They're not just making $65, it's $65,000. 10 times 8 would be 80. 12 times 6 would be 72. 15 times 3 is 45. Well, anything times 0 is going to be 0. And then for this last one, x times 18 minus x, we could write it as just x times 18 minus x, right? We could also distribute that if we'd like to, and that's what's going to happen in the next problem. But I want you to notice that the revenue increased to a certain point, and it started decreasing. This is very much like our perimeter versus area kind of problems that we've already looked at. So it's the same idea on that. It asks in number 2, is the relationship between the price of the movie and the revenue quadratic? So they're asking, is this quadratic? Remember, for quadratics, we're always looking for squares. And right now, I don't see a square. However, if I would take this and say x times 18 minus x, and I wanted to clean this up, I wanted to simplify it, I would have 18x minus, oh, there is my square, x squared. So yes, this is quadratic. I've got a square on my variable. That's the big giveaway right there. And then For 3, it says plot those points that represent the revenue. I will plot those very quickly. I also have them on the next slide. And then we want to make a decision for what we recommend that the company does. In fact, I think I'm just going to switch to the next slide and show you that graph right there. So here it is all graphed. Boom. And I'm just not going to quite show you the last answer here yet. But you can see this looks like a quadratic graph, right? It's increasing, it's decreasing, it's a curve. They have some points, obviously they don't have every single point as an option there, but you can see that quadratic shape that we get. Now the question here is based on the graph. Oh, actually I should go back here so you can actually see the question. It's on your paper, but it says, what price would you recommend that the company charges for a new movie? Remember, we want to maximize revenue. We want to make the most money possible. So when I look at this completed graph right here, clearly you can see that there's a curve, and I would want to find the very highest point, which we're going to call in just a second, that's a vertex. I want to find that maximum point. And here is my thought on this. Remember, we said 18.0 was one of our points. So right here, this is actually at 18.0. Does everybody understand, I hope, that we would also have 0.0 as one of our points? Because if you have 0 for a price, you're going to make $0 for downloads, right? So 0.0. So if I wanted to find the actual maximum, I know right now it looks like at $10 I might have the maximum. I don't think that's actually the maximum because we don't have all of the points graphed. If 18 is the maximum, or I'm sorry, if 18 is where it gets back down to 0, then halfway there should be the maximum, right? We should have some symmetry here. So I would say that we should be charging $9 because at $9, we would have a little bit more profit. And in fact, if I put 9 in here for this x, 18 minus 9 would be 9. We already know that when the x and the y match, like if we were talking about the area again, we get a maximum. That would be at 81. So I know I didn't get my point quite perfect, but it's definitely going to be the maximum there because it's that symmetry, because it's the vertex, because when I have the x and the y match, that's how I can maximize this number. So we know that it would be somewhere between 5 and 10. It was on the uphill at that point. But again, $9 would be exactly halfway in between the 0 and the 18. So the function that uses this, we've got that 18 minus x. It's called the demand function, right? Kind of a supply and demand kind of thing. So this is the demand function. And the graph is known. That's what a lot of people in business are looking at when they're trying to decide on prices, for instance. Economists are interested in different factors that could possibly affect that demand function because there's just real world kind of stuff that can change that. So number 1 asks, what are some of the things that could increase the number of downloads predicted for the same given price? So if I don't change the price, what kind of things could get us to have more money? So, or to have more customers, I guess, that would be buying this. Here are some options, right? If we have movies that are just better, if they're more popular, if they're movies that people like, then we would have more downloads, right? The number of people who like watching movies could just increase. I'm thinking like during all of our lockdown stuff, there's a lot of people that were watching movies that maybe typically wouldn't have been watching movies, but that's something that they could do while they were at home, and it was a reasonable thing that they could spend their time on. The price of a movie at a movie theater could go up. So some people might really like to go to movies, but if it costs too much to go to the movie theater, they might be more willing to spend money on a download of a movie. Number 2, if the demand shifted so that we predicted this would be our new function or way to figure out how many thousands of downloads would be we're predicting based on this, what do you think would happen to the price that gives you the maximum revenue? All right, so now instead of 18 minus X, we're talking about 20 minus X, which means that my graph would get back down to the X-axis at 20, 0 instead of at 18, 0. So then finding the middle of that graph, that means that $10 would be the maximum that I would have for that instead of the $9 that we said would have been the maximum. Okay, so this is what that graph looked like, just kind of spread out a little bit better, but this is like actually labeling. So we had $0 for zero for the price. If the price was $18, we would have $0 of profit. And if it was at $9, that's where we get up to this maximum. Remember, we said that that was going to be at 81, and you can see it's just barely over 80. Okay, so some things about this. This shape is called a parabola, right? This is what a quadratic looks like. That shape, again, is called a parabola. And we have some specific things that we're going to be looking at in the actual graph of these quadratics. Domain, vertex, and zeros are the things that we're going to be looking at. We've been talking about those, but not specifically using those words. So I'll talk about that more specifically on the next slide. But again, the 0, 0 and the 18, 0, that's going to be finding the zeros of the functions where our revenue, our profits are down to 0. The vertex is that highest point. And the domain, we've already talked about the word domain in the past. Not even in this unit, like previous units. Domain is what the x's can be, what the x's make sense as. So for instance, in this graph, I would only be looking at a domain from 0 to 18. I wouldn't want to go any more beyond that because after $18, if it costs $18 for a download, they're saying they're not going to make any money. Why would you charge more money for the download? Why would you charge $19 or $20 if nobody's going to buy it? You'd be losing money after that because you can see the graph would go under the x-axis. Same thing, you're not going to have a price that's less than 0. The prices that make sense for this graph are from 0 to 18. So domain is just what's appropriate for the x's in a given situation. So those are the inputs, remember. So we were looking for the upper and the lower limits and where it would make sense to have our x's. We don't want to have a graph that's way too big and have information there that doesn't make any sense for what we're doing. And we don't want to have a graph that's too small and eliminate some of the information that we actually need. The vertex is that maximum or the minimum point on a graph, the very tallest that it gets or the very lowest that it gets. And then the zeros are where it crosses the x-axis. So they're really the x-intercepts. So let's take a look at this graph. I'm going to move this up a little bit too. So this is the area of a rectangle. We did this. We did a whole bunch of these. We just didn't write it out exactly the way this looks. Remember again, this function notation, this is saying the area based on some number that we use for x. A lot of times we were just saying that's what the y is, right? X times 25 minus 2x all divided by 2. That's the length times the width, basically. The domain in here, again, that's looking at what x's make sense. On this graph, this is, it's not crossing exactly at a whole number, but halfway between 10 and 15. This is at 12.5 and 0, and this is at 0, 0, right? The x's that make sense are between 0 and 12.5. After 12.5, we start to move into negative y values, and we're talking about the area of a rectangle. I can't have a negative area. So the domain here would be between 0 and 12.5. You can write it that way, or kind of the fancy math way to write this would look like this. 0 is less than x is less than 12.5. And actually, I'm going to choose to not put the equals, like not less than or equal to, on each of those, because if I had a length of 0, I don't have a rectangle. I have a width of 0, which is what would happen at the 12.5, I wouldn't have a rectangle. So I don't want it to be equal to those numbers, but somewhere between 0 and 12.5, that's where all of this stuff is graphed, right? The vertex, the very tallest point that I have on this one, it's a little bit difficult to know exactly just from looking at the graph, so we might have to make some calculations here. But remember that this is saying that we've got a perimeter of 25. Remember we said that the biggest area that we can get is when I've got a square. A square is when I have 4 equal sides. So instead of saying, well, 12.5 divided by 2, which is going to give me the same answer, I could say 25 divided by 4 gives me 6.25. That's what the x should be at my maximum area that I'm going to get. And then if I would substitute in that 6.25 into my equation right here, let me switch colors just so it's a little bit easier to see. I'm going to have y equals 6.25 for the x, 25 minus 2 times 6.25 is going to be 12.5 all over 2. Oh, I made my parenthesis wrong over here, sorry. So that's going to be 6.25. 25 minus 12.5 is 12.5, and 12.5 divided by 2 is 6.25. And again, if it's a square, that makes sense, right? The length is 6.25, the width is 6.25. When I multiply those, the area that I get for that is going to be at 39.0625. And I can see we might want to round that. The vertex then would be, the x was 6.25, and the y part was that 39.0625. That's how we'd find the vertex. Clearly, if I'm looking at this graph, I can see that the vertex height is a little bit under 40. So if you would guess 40 or 39, that would probably be fine. The zeros of the function are just where it crosses the x-axis. And usually we don't have zeros as ordered pairs. I just want to know what the x's are that make the y equal to 0. So I would have a 0 at 0, and I would have a 0 at 12.5. Yeah, and I guess I was done with that one. All right, same exact information here, a new graph, a new situation. So this is talking about the number of squares in a function. In a step function, we've looked at so many step functions, and our step function is saying n squared to the step squared plus 4. And again, remember that when I have this f of n, that's just really saying what the y value is equal to, right? The domain for this, it looks like I could graph kind of anywhere. But remember, this is actually talking in this situation about a step function. I don't have negative steps in a step function. I can have 0, but I don't have anything that would be negative. So my step function, the x or the n for the step function, would have to be greater than or equal to 0. So that means really here, this part of the graph has no meaning. If I just graphed y equals n squared plus 4, that would be the entire graph. In this situation, the left part of it, the negative x values, don't make any sense. So I would not have that as part of my domain, okay? The vertex on this is right here, and that point is at 0, 4. And I'm not just guessing that, it's because 0 squared is 0 plus 4 is 4. So the y part was 4. The vertex is at 0, 4. And that means, again, at step 0, I already had 4 squares, right? We had some of the step functions that had something there, and then we started adding like 1 squared and 2 squared and 3 squared. The zeros for this function, there aren't any. It doesn't touch the x-axis. So there are no zeros. And again, that's because there's never a time when there aren't any squares in this. I start with 4 squares and it never gets lower than that. Okay, here's another one. The distance in feet that an object has fallen, however many seconds after being dropped. Okay, the domain again, thinking about what this actually means. Now remember, this is not the path of something that's fallen. It's talking about how far it has fallen. And when we're talking about time, I am not going to have a negative amount of time. I don't have negative t values here. This part of my graph doesn't make any sense. It can start exactly at 0, so my domain could be from 0 on, so that would be at, the time would have to be greater than or equal to 0. And realistically, eventually something's going to hit the ground, right? So I can't see where it's going to stop because I don't know what the original height was on this or anything like that, but this is just how far it has fallen. So I could have just positive t values. The vertex, you can see it's right at 0, 0. That just means that at 0 seconds, it hasn't fallen yet. You're still holding on to it, right? And then the zeros for this function, it's also at 0. And again, because that means at 0 seconds, it has fallen 0 feet. One more of these. So this is talking about the height of an object now. And again, this is not the path that it's following. This is just the height that we're talking about. And this one again is talking about time. So I do not even want to consider this part of my graph. It doesn't make any sense to have negative time. This time though, I do have an ending point of this because I can say, okay, at 0 seconds, I know exactly where it's starting, but it actually shows when the height gets down to 0, which is when it hits the ground right here. So really the only part of my graph that I want to look at is that. From 0 to 6 seconds is the only domain that makes any sense. It could be exactly equal to 0 seconds. It could be exactly equal to 6 seconds or anything in between. The vertex is going to be, the time is going to be 0 at the tallest point that this is at, and the height is at 576. I'm hoping that you can see where I'm getting that number from, right? This was the initial height. That's where we started. If I would put a 0 in here for the t, that whole thing would turn into 0, and 576 minus 0 is 576. The zeros of this function are just when the time is equal to 6 seconds. So at 6 seconds, it hits the ground, or it reaches the ground. So it has 0 feet of height at 6 seconds. All right, so those are several examples looking at all the different parts of a graph. This is the summary that you have. Quadratic functions do come up when we're talking about revenue, even though we didn't do a ton of revenue stuff. We did talk about that several times. If we're going to be selling raffle tickets, we've got this graph down here. It says decide how much to charge for each ticket so that we know, right? So again, if the tickets are really, really cheap, you'll sell a whole bunch, but you won't make as much profit. If the tickets are really expensive, very few people are going to buy them. But you want to find kind of that sweet spot in the middle where we can make the most money. So here's the graph. And it would make sense then that, again, the revenue is going to go down after a certain point. But I can see that if I get 0 here and I get 0 here, 4 is going to be my maximum. And if I would substitute a 4 in right there for the dollars, I would have a height, and I've already worked this out, to be at $1,200, right? So if you charge $4 for each ticket, they're going to make a prediction. Oh, and it's right here. They're making a prediction that they would make $1,200 in profit. And again, the domain here only makes sense to between 0 and 8. The graph would continue under the x-axis at that point, but we wouldn't want a negative revenue. So we wouldn't charge less than $0, not even possible. We wouldn't charge more than $8 because we would have negative profits or negative revenue. So that doesn't make any sense. All right, last thing then. Just in general, when we're talking about the zeros of a function, we're talking about basically the beginning and the ending of a situation that makes sense, right? So for example, when you, like what you would charge for those raffle tickets, or when something that's dropped would hit the ground, those are the zeros of a function. The vertex tells us the maximum or the minimum for whatever we have here. So the maximum profit would be at the vertex if it was an upside down U. If it was like that step function one, we'd find the minimum, like how many squares we started with, for instance. And the domain, again, is just the x's that make sense in that situation. So you could look at an entire graph, but we might look at, because it's a certain situation, and say, oh, part of this graph doesn't even make sense. All right, you'll probably be doing this together in class if you're in class, but here is another one of these models, right? We've got this price. Based on this model, which price would you generate more revenue from if you charged $5 or if you charged $17? So $5 would be about here.
Good morning, Ben Franklin.
And 17 is right there, clearly. 5 is more. And I'm going to stop the video at that point, even though we haven't answered the last two questions. If you need any help, talk to your math teacher.